bunch of different confidence intervals. If I made 100 of these confidence intervals following these same steps, I take a random sample, observe the sample mean, sample standard deviation, follow these steps to make a confidence interval. If I do this 100 times, I expect 95 of those confidence intervals to actually get the true value of mu within the interval. But because of the nature of random sampling, 5% of the time, I'm going to get a sample that misleads me, quote, misleads me into believing, into getting the wrong confidence interval, okay? So just, if that's hard to understand, imagine that picture of the dog and the invisible owner, okay? Based on what we know about the dog and the owner, if I took a whole bunch of pictures, 95% of the time I can say the owner's within 2 yards of the dog. Okay, or actually I can all the time, if I did this 100 times, I would expect about 95 of those times the owner is actually within 2 yards of the dog. But about 5% of the time, I happen to take the picture at the, quote, wrong moment where the dog was more than 2 yards away from the owner. Okay. Same type of thing happens here. 95% of the time, our samples will, quote, behave well enough that when we follow the process of making a confidence interval, our confidence interval will get the true value of the population. But about 5% of the time, because of the nature of random sampling, our sample might be unusual enough to mislead us about, or to give us the wrong confidence interval. Does that make sense? Okay. And the thing is when you make a confidence interval, you don't know if you're in that 95% or if you're in the 5%. You never know. Okay? So what does it mean to be 95% confident? Okay. If we took many random samples, expect 95% of our samples to produce contain the population. Because of randomness, give us hope that yes.
Okay, so I understand all that. But the connection I don't fully see justified
Okay.
is before we were talking about, I wrote in my notes, we know that the sample means follow a normal distribution. And that was true, but when we were looking at a lot of samples, like different, they only follow the normal distribution when we were looking at multiple samples. Like one sample doesn't in and of itself necessarily follow normal distribution.
Okay, actually, one sample does follow the normal distribution. It comes from the normal distribution. The reason why in our simulation here, I did like 10,000 of these things was because I was trying to use the histogram to illustrate what the distribution looks like.
Okay.
Okay? So each individual one of those samples actually came from a normal distribution.
Okay.
But in order to show that, I had to get a whole bunch of samples. Okay? So we know that human height, like the human height follows a normal distribution. Okay? So if we did, like if we want to talk about the height of women, we know that follows a normal distribution. But if I take one random woman, that will not be a normal distribution. It's just one observation. Okay? And if I wanted to see what a normal distribution looks like, I would have to take, 1,000 or 10,000 random women, and then if I made a histogram of all of the different heights I observed, then it would look like a normal distribution. But that's only because we're making a histogram based on all of our samples.
So what does it mean for a sample to follow the normal distribution if it doesn't?
That means if I draw one individual sample, or one individual person, or whatever, that value comes from the normal distribution. So it basically it tells us, the probability that that value is going to be large or small follows the normal distribution. The distribution being all possible values that exist. So it's okay to say one draw comes from the normal distribution. Okay. One draw in of itself is not a distribution, but it's okay to say it comes from the normal distribution. It's a little okay, let's just simplify this a little bit, okay? I can say a coin lands heads 50% of the time, okay? But when I flip a coin, how's it going to end up? It's going to be heads or tails. It will never actually be 50% heads, okay? Does that mean the coin flip doesn't follow 50% heads? No, the coin flip is 50% heads. The result I get comes from that probability. But in order to see that actually happen, I have to take thousands of random draws.
The reason I'm confused is because when you're doing one sample, and let's say the population isn't normal, but you're still saying the sample follows a normal distribution.
The sampling distribution. The sampling distribution
that one's
of
normal.
The sample mean. Yeah, comes from the normal distribution if those central limit theorem conditions are met. So, which was if the samples are drawn independently and random, if the sample is not too big and if the sample is not too small. The one that usually gets us the most often is the sample being too small, okay? Or the sample not being random. In the book, it's easy to have random samples. In real life, difficult. I hope that.
Well, when we're looking at the sample distribution picture, can I call that a histogram?
Okay, yeah.
Okay, when you look at that, and like before, basically like the range got shorter, right? And so, but for whatever reason, it still follows that 95% of that histogram includes the mean of the original population?
No, we're not talking about the sampling distribution itself, okay? A confidence interval. So the sampling distribution is the distribution of y bars or sample means. That's what the sampling distribution is, okay?
Yeah.
That's separate from a confidence interval, okay? A confidence interval is just a high value and a low value creating this range, okay? That's all a confidence interval is. The way we created a confidence interval or came up with this formula for a confidence interval is based on our understanding of sampling distributions, okay? But the sampling distribution is
but they're not directly related.
They're not the same thing, okay? The sampling distribution is a normal distribution, and it's the distribution of the y bars of all the different samples we can get, okay? Confidence interval is just a high value and a low value saying I'm 95% confident or I'm 90% confident that the population mean is between these two values. How did I come up with these two values? It comes from our understanding of the sampling distribution. But that's it. That's the only connection between the two, okay? Confidence interval, I just have from here to here, I'm 95% confident that population mu is between these two numbers. And that's it, okay? Is that okay?
Yeah, class is over. I don't know.
Oh, is it over? Okay. All right. Well then.
I'm ending it. I'm just kidding.
Okay. Then we are done. The book goes into some of these topics a little bit more. I think the homework will give you some good practice with it. Okay.